In this lecture, we're going to talk about the core theorems of basic analysis. They're the building blocks of our theory from this point out, and it is where most of the work we've done has been aiming at up till this point. So let's get started. We'll have some definitions. Okay. Let f from the open interval ab to r be a differentiable function. Suppose that c element of ab is a point such that for some delta greater than 0, f of c is less than f of x for every x between c minus delta and c plus delta. Then we say that c is a local minimum of f. If instead f of c is greater than or equal to f of x for every x between c minus delta and c plus delta, then c is a local maximum for f. If c is either a local maximum or a local minimum, then we refer to it as a local extremum. All right. So this now brings us to Fermat's theorem on extrema. Okay. Suppose that f from the open interval ab into r is a differentiable function. Suppose that c in the open interval ab is a local extreme point of f. Then f prime of c is equal to 0. Okay. We will prove this by proving the contrapositive. We will show that if f prime of c does not equal 0, then c is not a local extreme point. So let's first suppose that f prime of c is positive. Okay. Since f is differentiable at c, f of x is equal to f of c plus f prime of c times x minus c plus u of x, where u of x divided by x minus c has a limit of 0 as x approaches c. So this is just, definition of differentiable stuff. Therefore, if we take the limit of the difference quotient minus f prime of c as x approaches c, then f prime of c is equal to 0. So take that and put it in your pocket. All right, now let's continue from here. There is a delta greater than 0 such that if 0 is less than x minus c in absolute value is less than delta, then the absolute value of the difference quotient minus f prime of c is less than 1/2 of f prime of c. So recall that we presumed that f prime of c was positive. It now follows that by a little arithmetic that negative 1/2 f prime of c is less than the difference quotient minus f prime of c is less than 1/2 of f prime of c. Again, do some more arithmetic by adding f prime of c to each of the three pieces of the inequality. We get that the difference quotient is then between 1/2 of f prime of c and 3/2 of f prime of c, which all we need from that is that the difference quotient is positive whenever 0 is less than f absolute value of x minus c is less than delta. Okay. Now, to conclude the proof, if c minus delta is less than x is less than c, then f of x minus f of c is less than 0. So f of x is less than c. Therefore, we know that c is not a local minimum for f. On the other hand, if c is less than x, is less than c plus delta, we know that f of x minus f of c is greater than 0, and so f of x is greater than c, therefore c is not a local maximum of f. It follows that that c is not a local extreme point. When we consider the case f prime of c is less than 0, it will follow that similarly that c is not a local extreme point, and so this ends the proof. Okay, so this is the most technical proof that we will have. All of our epsilonics have been rolled into this, everything that's tedious. From this point on, we will be making use of this theorem to prove our other results. And so we'll first start with Rolle's theorem. It's actually a lemma. Suppose that f from the closed interval AB to R is continuous, and that f prime is defined for every x element of AB. Suppose that f of A is equal to f of B. Then there is a real number c such that f prime of c is equal to 0. Okay. Now, let's first suppose that f of x is equal to f of A for every x element of B. If we do make this special case, then if we let c be equal to a plus b divided by 2, we're done. Okay. We may now assume that f is not constant. If f is not constant, there are points capital M and little m not equal to each other, such that m is the maximum of the function f on the interval, and m is the minimum of the function on the interval. At least one of the big M and the little m is not equal to the common value of f of A and f of B. It shows then that there is at least one extreme point in the interior. Therefore, by Fermat's theorem on extrema, f prime of c is equal to 0. Boom! We're done. Okay, so from Rolle's theorem, we'll roll right ahead to the mean value theorem. Suppose that f is a closed interval, is a function on a closed interval AB to R. It's continuous, and that f prime of x exists whenever x is between A and B. Then there is a real number c such that f prime of c is equal to f of b minus f of a over b minus a. Okay. To do this, we just define f of x to be a function which is the difference between our function f and the line which interpolates it between the point A and the point B. Okay, that's all this is. This is just calculating the directed distance between the line and the function. Okay. And so right here we have this secant line, this interpolating line. We take the difference. Notice that f of A is equal to 0, which is equal to f of B, because it's an interpolating line. It agrees at those points. Also notice that if we take the derivative, okay, then it's we can calculate that easily, that capital F prime is equal to little f prime minus this constant. By Rolle's theorem, there is a real number in the interior such that f prime of c is equal to 0, so it follows that little f prime of c must be equal to the difference quotient, and so we're done here. This was to be proved. We're now brought to some corollaries. Okay, first suppose that little f from the closed interval AB to R is continuous, and its derivative exists whenever x is between A and B. If f prime of x is greater than or equal to 0 for all x in a, b, then f of a is less than f of b. So basically, this is what you would expect. If your derivative is positive, your function is sloping up, and so you're no smaller at the beginning than you were at the end. So by the mean value theorem, okay, there is a number in the interval a, b, so that f prime of c is equal to the difference quotient. Then just by arithmetic, we have that f of b minus f of a is equal to f prime of c times b minus a. Since f prime of c is greater than or equal to 0, we can, and that f, since f prime of c is greater than or equal to 0, it will follow therefore that f of b minus f of a is greater than or equal to 0. Therefore, f of a is less than or equal to f of b. Another corollary, if f prime exists and is positive on AB, and if x1 is less than x2 are elements of AB, okay, then f prime of x is greater than f2 of x. So this is just a little bit more than what we had before. The derivative exists and is positive. So let's take a look. Note that f is continuous on the closed interval from a to b, and f prime of x is positive on that interval. There is a real number between them, so that the derivative of c is equal to that difference quotient, and so we've actually sharpened the previous result. The proof goes through virtually the same, and it will follow that f of x2 will be greater than f of x1. All right, now for our last corollary. Suppose that f and g are differentiable on the closed interval ab. If f of x is equal to g of x, and f prime of x is less than or equal to g prime of x for every x on the open interval ab, then f of x is less than or equal to g of x for every x in the closed interval ab. And here again, just let h be a new function, which is the big function minus the little function. All right. It will follow that the derivatives the derivative of f is the difference of the derivatives, and that they must be positive, okay, from the previous result. Therefore, well, not from the previous, but from our hypothesis. Therefore, h of x is greater than or equal to 0. But that comes from the previous result, and therefore we have f of x is less than or equal to g of x for a less than x less than b.